Myself, Mr. Akshay Kumar Surde, Assistant Professor, Department of Mechanical Engineering. Today, we will derive the expression for the shear stresses in rectangular section. Learning outcomes: at the end of the session, student will be able to calculate the shear stress distribution and identify the maximum shear stress across the depth of a rectangular beam. Secondly, interpret the parabolic distribution of the shear stress across the section and recognize that it is 0 at the outermost fibers. So, let us discuss the shear stress distribution in rectangular section. So, consider a rectangular section having width B and depth D, and this rectangular section is subjected to shear force F. So, F is the shear force acting on the section. Now, shear stress at any level, it is given by tau is equal to F into A y bar divided by I upon B, where F is the shear force acting on the section of the beam, A it is the area of the portion which is above the level at which you are determining the shear stress, y bar is the distance of the CG of the portion which is above that particular level from the neutral axis, I it is the moment of inertia of the given section about the neutral axis, and B is the width of the level at which we are determining the shear stresses. So, let us consider a level EF at a distance y from the neutral axis, and therefore, the portion which is above this level EF is shown by EFCD. So, this is the shaded portion which is above the level EF. Now, as the section is rectangular and it is symmetrical about x and y axis, the neutral axis of this particular section is lying at a distance d by 2 from the top edge and from the bottom edge. So, the position of the neutral axis is at d by 2 from the top and bottom. So, B it is the width of level EF at which we are determining the shear stress. I it is the moment of inertia about the neutral axis, and F is the shear force acting on the section. So, let us calculate A into y bar. A into y bar is nothing but it is the moment of shaded area above level EF. So, first of all, we will calculate the area of shaded portion. So, width of the shaded portion is B into depth of the shaded portion. So, depth of the shaded portion can be obtained by d by 2 minus y. So, depth will be d by 2 minus y. Now, y bar is the distance of the CG, of shaded portion about the neutral axis. So, first of all, I have to calculate the depth of the shaded portion. So, depth of the shaded portion is nothing but d by 2 minus y. Half of that I will get the CG of the shaded portion, but we have to calculate this y bar from the neutral axis, therefore plus y. And by solving this equation, you will get d by 4 minus y by 2 plus y. So you can solve this equation, d by 4 minus y by 2 plus 2y, and hence y bar is equal to d by 4 plus y by 2. Hence get 1 by 2 outside the bracket, 1 upon 2 you will get d by 2 plus y. So putting the value of a into y bar in this particular equation number 1. So by putting the value of a into y bar, tau is equal to f into area which we have calculated, b into d by 2 minus y into y bar is 1 upon 2 into d by 2 plus y divided by I into b. Therefore this d by 2 minus y and this d by 2 plus y, these two brackets we can solve. F into b d square upon 4 minus y square divided by I upon b. So b will get cancelled. Shear stress tau is equal to F into 2I d square upon 4 minus y square. Okay. So for the given section, the shear force is constant. For the given dimensions of the beam, moment of inertia about the neutral axis is also constant. Depth of the section is also constant. So shear stress at any level varies according to the distance of that layer from the neutral axis, and the variation in the shear stress take place according to the parabolic curve. So if I want to calculate the shear stresses at various levels such as top edge, at the neutral axis and at the bottom edge, I have to put the value of y to get the shear stresses. Hence shear stress at the top edge of the rectangle section, that can be obtained by putting y equal to d by 2 in equation number 2. So when I put that particular value, shear stress at the top edge is equal to 0. Similarly, shear stress at the bottom edge, that can be obtained by putting the value of y equal to d by 2. Again, shear stress at the bottom edge is also equal to 0. Now shear stress at the neutral axis. So when y equal to 0, I will get the shear stress at the neutral axis. So by putting y equal to 0, I will get the shear stress at the neutral axis, and that is equal to F upon 2I into d square upon 4. So it will be F upon 8I into d square, where I is moment of inertia of the given section about the neutral axis, and that is given by BD cube by 12. Hence, putting the value of moment of inertia tau at neutral axis is equal to F upon 8 into BD cube divided by 12 into d square. So d will get cancelled. You will get 12 upon 8 into F upon b into d, where b into d is nothing but the area of this rectangle section and F is the shear force. So by solving this equation, I will get 1.5 into F upon B into D. So, F upon B into D is nothing but average shear stress, and hence shear stress at the neutral axis is 1.5 times of average shear stress, whereas average shear stress is shear force acting on the section multiplied by the area of that particular section. Now, we will discuss the shear stress distribution diagram. So, shear stress distribution diagram is drawn across the depth of the section. So, at the top edge shear stress is 0, at the bottom edge it is 0. So, at the top and bottom it is 0, and at the neutral axis it is 1.5 times of average shear stress, and it varies according to parabolic curve. So, from 0 at the top edge the shear stress goes on increasing and it is maximum at the neutral axis, and that is 1.5 times of average shear stress, and from its maximum value it goes on decreasing to 0 at the bottom edge. So, shear stress distribution or shear stress varies according to the parabolic curve across the depth of the section. This particular material is referred from a book of strength of material by Dr. R.K. Bansal and S.S. Bhavikatti. Thanks.